Thank you.
Excellent. So I'm very pleased to welcome Peter Bickel as our last speaker before lunch, which as usual is right next door in Wilson Court. And I would just say that Peter will be giving another talk later in August as the Rothschild visiting professor for the program. So welcome again, Peter, and thanks for joining us.
Thank you, Patrick. I hope this talk will not keep you from lunch too long. Again, as many of these talks have been, this is going to be about block models, and we know they're not terribly good approximations to what one sees, but on the other hand, they're somewhat interpretable, and even crude interpretable models can be useful. So here's the outline. I'm going to give an introduction to general network models as I see them, as one would like to have them, then block models. And I'm going to talk about profile likelihood, in fact, and variational methods, and mean field likelihood. Asymptotics for these methods, why I want to consider likelihoods, some I found surprising simulations initially, and an approach to possibly getting by the surprises. So my definition of a network is simply a representation of a set of data objects, people, computers, genes, exhibiting relations between pairs of such objects, friendship, communication, regulation. And then, usually, covariates are present. In fact, if they're not, I think we're usually in trouble. That is, properties of the objects, educational, economic, location, and properties of the relations, strength and type. So, for example, this is taken actually from a very recent paper of Mark Newman and Aaron Clausette. This is actually ecological data and from the Weddell C web, and you have basically organisms of different types, and you know whether A eats B. And so this is actually initially a directed network, but you can disregard the directions for to begin with, and see what you can get. And in fact, Mark and Aaron did get something using a rather natural covariate that comes with this web. And then brain networks, which are for example, functional MRI recordings. There are actually two networks. There's the physiological network, which in a very some crude way corresponds to the functional network, and usually one sort of tries to divide up the structure into pieces and then looks at functional recordings of different kinds between connecting the pieces. The formal representation I'm going to talk about is again, pretty much as many of the previous speakers have spoken about. You have xi, which are node covariates, xij, which are edge covariates, or wij, which are edge covariates, such as, let's say, the strength of the connection. And then there's the symmetric adjacency matrix, which is what most of the talks have been about, which have not had xi's and wij's present. So in the Weddell C, you have xi, the xi that was actually used by Newman and Clausette is body mass, but there are others, like the type of organism and so on, and other information. And then with fMRI, you have, for example, the strength of the connection between the nodes, which are equal to parcels, equal to brain areas. And then there are other covariates. For instance, we're studying Alzheimer's patients, and then another covariate would be plaque deposits, which is measured in a different way. I'm just giving you these as examples. So the general model that one might think about is, two directions. One comes from original model proposed in the social sciences by Huff, Hancock, and Raftery, and then the Aldous Hoover model, which you've heard about, is that you have this vector of latent variables Z, one associated with each node. And then what you observe is X, which is n by p, the covariates, one possibly a vector for each node, vector W of edge covariates, and then this and the adjacency matrix. And now you make the big assumption that ZIs are independent latent variables, and in both of these models you have the assumption that the conditional probability that you have a link, given the full mess of latent variables, observed covariates, is a function only of the latent variables belonging to I and j, the covariates belonging to the covariate vectors. There should actually be the covariate vector belonging to I and j here. Somehow it got missing, and the Wij's. And those are big assumptions, and basically what Hancock and Raftery did is they introduced a parameter theta, right? So you have a parametric family here of these, which links the objects in this way. And the big assumption that's made already is that things depend only on, you have all this information, and that things depend only on your latent variables, so to speak. And of course, with Aldous and Hoover, no theta, no covariates, but again, this assumption well, I should be careful. Aldous and Hoover proved a representation theorem, and basically what these guys are, when you drop the theta and the x's and the w's, is things where you can actually, they're the extreme members of the representation. They're the ergodic guys, the guys that you can actually hope to identify from a single representation of the network. Of course, the representation is as a mixture, but you can never tell what the mixing measure is if you only have one observation of the network. Okay, and now we have the emphasis on communities, and we have the stochastic block model. Here you have the z's can be thought of as basis vectors. The one in the basis vector tells you which community you belong to, and these are assumed to be multinomial alpha 1, alpha k. And then you can write the probability that aij equals 1 given z as this inner product, which we've seen already with the conditional probability, which we've already seen in Arash's talk and others as well. From the statistical point of view, the parameters of interest being these b's, which are probabilities given that you belong to class, that I belongs to class A and J belongs to class B, the probability of having a connection. Then, of course, there are these other parameters which are not apparent here, but then come in later, which are the probabilities of belonging to class A and class B, which are, in other words, the marginal distribution of the Z. And then there's a nice generalization due to, there have been many generalizations, but there's a generalization which encompasses many of them, which appears in the paper of Zhang, Levine, and Zhu, where you can sort of think of the ZIs as being probabilities of belonging to that class. In other words, you can belong to more than one class at the same time. You can have overlapping classes. Nothing says that you can't have that.
But do you mean that to be Zij there?
Yes, because Zi is a vector, and so Zij is the probability that I belong. It shouldn't be Zij, it should be Zia or something like that. Belongs to class A. I'm sorry, the notation's bad. Okay, so the questions are, can these models be fitted so that the actual Z can be identified, asymptotically consistently estimated? From that, estimating B is usually very easy. And be generalized so that covariates can be built in. And the other question that I sort of want to implicitly address is, can we do this in practice as well as in theory? And that's the surprise I found in the simulations that we did. So I want to talk about two methods, both having to do with likelihoods. And why likelihoods? I mean, of course, spectral clustering is the preferred method that we've heard discussed in many of the other talks. Well, the nice thing about likelihoods is that the covariates are easy to build in. So if, for example, as in fMRI recordings, you have networks for each of a number of individuals, right? You can think of those as IID. You would like to put them together. Easy to do with likelihoods, not so easy to do with spectral. Or not so clear how you do it with spectral. I mean, you saw one approach with Sharmo, but somehow it's sort of automatic, and you can build in covariates rather automatically as well. And that's a big advantage. And I'm going to talk about block models in some sense as block models with covariates as some sort of approximation to general model. So if you think of the block model log likelihood, given the z's, then you can write it out in the way indicated. And let me get the marker. Right, this is the part which is coming from the marginals. This is the part that's coming from the conditional distribution. Actually, the conditional distribution of given the block memberships. And this is written in canonical form for the exponential family. So the parameter, rather than being BAB, which is the probability of an edge given I is in A, J is in B, is in terms of theta AB, which is the canonical parameter for the binomial. So the z's are a dependent multinomial, alpha 1, alpha k. The alphas are not known. And the profile likelihood is simply you take this thing, this log likelihood actually, where of course we don't know the z's. That's the whole problem, right? If we knew the z's, this would be easy. And we maximize over the parameters in some sense of interest, which are the theta and the alpha. In other words, the probabilities of having an edge between A and B, and the probability of belonging to community A. And if you do that, you get actually a function which is a function only, of course, of the z's. And that's what the profile likelihood is, right? Because those parameters can be estimated easily, right? If you knew the z's, no problem, right? I know how to estimate the probability of belonging to A. I simply count. And I know how to what the probability of communication is as well. And there they are. And then you plug them in to the log likelihood, and you get a function of the z's. And that's the profile likelihood. And what actually, in a paper in 2009, Ayu Chen and I showed in examining this and viewing this as a modularity, as well as the Newman-Girvin modularity, showed that, in fact, if you have a finite block model, if the degree, for example, grows, well, I guess I'll get back to asymptotics a bit later. But that's a likelihood that one can use. The only problem is, of course, it depends on z, and what you really want to do is you want to maximize this thing over all z's, which is a combinatorial problem. Another approach, which I guess came from physics really, is the so-called variational likelihood. So again, you have z's, which you don't observe, the latent variables, which are now tell you the memberships in the blocks. And you write down, you play a trick, you write down the logarithm of the probability of what you can see, which is A. And this is the log of a sum over all possible assignments to blocks. And then you introduce this oops, sorry. Let me go back. Oop. No, dear. What do I want? I think I'm going the wrong way. Yes, I am going the wrong way. Variational electric, yes. So what you do is you simply introduce a marginal probability on, or a probability on all, on the joint z's, z1 through zn. Call that C. You introduce it top and bottom, and then you would just simply apply Jensen's inequality, and you get a bound, right? You get a bound on the logarithmic, on the logarithm of the probability of A, which is this function of C. And any choice of C is a lower bound. And there is actually, this is perfectly nice, because there is, of course, a choice of C which will give you identity. And that choice is taking C to be C star, which is what you don't know, of course, which is the conditional distribution of Z given A. But of course, that doesn't help any, right? So you actually have a representation. The log of P of A is the maximum overall Psi of this expression, but this is maximum over the space of all possible probability distributions of this n-tuple. And the mean field method says, well, let's use something that we know isn't true, which is let's pretend that this thing is a product measure. But a product measure for each, a different possible product measure for each, you can have a different marginal for each coordinate, for each Z. And then you write down this likelihood, and it turns out to be this is actually, you bring in the probabilities of assignment to the blocks, which again vary from individual to individual. And in the end, you maximize overall possible choices, and you get this expression. And so what you now are left with is something which looks very innocent. You simply need to maximize over all possible pi, and the pi's are, you have a k-dimensional parameter, or k-1 dimensional parameter for each I. So you actually have n times k-1 parameters. And doesn't look too bad. You can, in principle, do it. And that's the mean field method. It is a lower bound. I mean, the function that you're optimizing is a lower bound to the function you want, but that doesn't tell you very much about the maximizer. Still, this does give you a likelihood, right? Which has all these advantages. And now you can study this, and one way of studying it is to reparameterize, as been seen already, so I'll have to jump because I'm already at 5 minutes before the end. So you basically reparameterize in such a way that you bring in the unknown distribution of the z's, which in this case is a discrete. The z's are now discrete for the block model, but you parameterize in such a way that you bring in the probability of edge, which permits you to have the graph be sparse. So you have lambda n equals big O of n, which is dense, where you just assume that the probability is of order 1. Semi-dense is that the average degree goes to infinity faster than log n. Semi-sparse is it simply goes to infinity. And then the regime that, of course, all focus has been on in probability theory, which is the sparse regime, where it's of order 1. The problem is, from a statistical point of view, that's a very unpleasant regime, because you cannot estimate the parameters that you want, in fact, because there are all these even in the block model, because there are all these sparse all these isolated points. Let me just tell you a feature of the semi-dense regime, which is rather nice. So if the average degree goes to infinity faster than log n, then it follows actually from my work with Ayu Chen that there is an algorithm, in fact, profile likelihood, not an easy algorithm because it involves combinatorial optimization, such that with probability tending to 1, you assign everybody correctly. If you have k blocks, k is bounded, then you can actually assign everybody asymptotically correctly to their block. And this has an interesting consequence, which was shown separately by Dave Choi, Chang and Zhang and myself, and by Celis under fully dense conditions and also only for some of the parameters. You can show essentially the following. You can show that more or less in this dense regime, because of the fact that you can label things correctly, right, just knowing the A matrix, that essentially the situation is as if you knew the labels to begin with. Right? We have this algorithm which says from the data you can label things correctly. Well, as far as from the likelihood point of view, you might as well really just look at the log likelihood of the data with the labels. And that, of course, makes life very easy. And it holds not only, and this is rather nice, for the maximum, for the likelihood itself and maximum likelihood, which of course is incomputable, right? It also holds for the variational likelihood, which we have an algorithm for. You can maximize in this regime. And actually, more is true. Well, one consequence of this, which is rather nice, is that again in this regime, with probability tending to 1, the mean field likelihood and the profile likelihood are actually equal, which is somehow related, I think, is somehow analogous to the well-known result that if you want to do linear programming, you use the simplex method. That's an exterior, that's a method where you walk around the vertices of the simplex. That's what corresponds to profile likelihood. And mean field is an interior method, and in principle will lead you to the same thing. So this is very encouraging, right? At least to me it was very encouraging. Actually, you can show a little bit more recently, which I'll skip, that in fact, in principle, if the degree goes to, average degree goes to infinity faster than log n, you have an equivalence between the log likelihood, the mean field log likelihood, and the maximum likelihood, if you want, and the likelihood where you know the labels, but only in a rather weak sense. So I'm just going to skip that. So theoretical features of the two likelihoods, they're easy to incorporate covariates, as I mentioned, and this was done for the marginal by Newman and Closet. The asymptotic behavior you understand something about. Dave Bly and collaborators have shown that in principle it's possible to take the mean field likelihood and speed it up so that you can actually deal with large graphs. Special case was done by Ball, Carr, and Newman, and showed that you could, again, use non-combinatorial fitting to block models and degree-corrected block models. Well, we did simulations, and actually others have done simulations which suggest that there are real problems. Thank you. I think I can get to the main point of this.
You don't want to end with disaster.
No, I don't, and I'm not going to end with disaster. So what this shows is that mean field actually can have serious problems. And the problems come from the fact that although we understand the behavior of the maximum, the true maximum of the mean field likelihood, right? It behaves very nicely. Unfortunately, it's very difficult to find because there are all these bloody local maxima all over the place. And the local maxima can be very bad. So here's mean field for disconnected two-block graph with growing average degree. And here is the misclassification rate, actually. And the colors correspond to average degree size. And this is all 1,000 nodes. So with average degree 25, the misclassification rate of mean field likelihood with huge number of starting points is terrible. It gets better, indeed, as the graph gets denser, as things get denser, but there's potentially a problem. So what do you do? And so finally, I can show you that there is a way of getting out of the disaster, we hope, which we've just started to explore, which is, I mean, there are other ways too, but I presume, but at least the way that we are looking at is patching things together. So what you do is you select at random, I mean, actually not, what you do is actually select neighborhoods at random, but there's a result which you select at random. You choose subsets, which are relatively small, subsets of nodes which are relatively small. Now you can apply mean field, actually you can also apply spectral in this case, and so on. And everything is wonderful because you are not estimating 1,000 parameters, which is what mean field is trying to do. Right? You're only estimating 100 parameters. And you have still a large set of observations. And now the problem is, however, how do you put these together? Right? Because each one of them does a classification job, which is not perfect, but not too bad. But it could be, for example, that you have a vertex which is at the intersection of two of these graphs that you've selected. And one of them says that this should be class 0, and the other one says it should be class 1. Well, Sumendra Mukherjee and Purna Sarkar figured out this very nice way of basically having fitted one of these small guys, you construct something which does not depend upon the permutation but potentially problematic assignment of membership to blocks. And that is, you form the matrix which tells you how often things, or estimates how often two guys are in the same block and how often they are in different blocks. And then you put these together for all these guys, and you get a rather good estimate of this matrix. And now you do spectral clustering or something like that. And that seems to work rather well. And that's the end. Well, there's some theorems. Here's the end. Simulations show that this method really works quite well in situations for spectral clustering. Spectral clustering bombs, spectral clustering applied to the whole graph bombs, mean field clustering applied to the whole graph bombs. This reducing things to estimating small numbers of parameters seems to work. And I'll end with that.
Thank you. Questions?
Carl.
Did you compare with regularized?
Yeah, no, this was regularized.
It was regularized.
It was
If you
regularized.
compare this to regularized, it beats regularized.
Yes, in unbalanced situations, but not badly unbalanced situations. 70%, 30%. Oh, this is a very simple situation, by the way, where you simply, have a probability of being of having an edge within a block and a probability of having an edge across blocks, and 2 blocks. Yes?
So when you're patching these things together, the nodes aren't in disparate subsets. There's overlap across.
Yes.
And then can you give more details how you have 2 fits and there might be a a label permutation issue?
Right.
How do you patch them
Oh,
together?
well, so the idea is that you look at the ZZ transpose matrix, which is invariant under permutations, and then you average that over all the pieces. So you just bypass the permutation problem.
Easy transpose across all nodes.
Yeah, that's right.
Okay.
That's right. That's Arash.
I hope I can convey over the distance. But when you reduce the size, you also reduce you get sparser, so you lose the density. So isn't that a problem? So you reduce the number of parameters, you also reduce the density of the graph.
Yes, that's true because you have a smaller graph, but it still is a better I mean, of course, each of these estimates is quite noisy, but it's much well. Actually, I should let Purna and Sumendra speak, but it just speeds things up tremendously and makes things. You just don't get into false optima.
So
Yeah.
I know we're running a little bit over for lunch, so maybe just one more question for Peter, and then we can continue over lunch.
Okay.
Okay. Let's
Lunch.
start there.